So basically, you're trying to use available energy and degrees of freedom fully over the networks. And one of the ways that you can do it very simply is, let's look at this very simple example again, 3 nodes, although instead of all going in the same directions as the one we saw this morning, we're going to do just basically a relay. I send A from the node on the left with the hope of getting it to the node on the right. And there's a relay in the middle. And then the node on the right sends B. So far, so good. The node in the middle has A and B. What do I generally do? I retransmit A for the benefit of the node on the right, and I retransmit B for the benefit of the node on the left. Of course, that's not what I'm going to do. I'm going to send A plus B. Because this guy already had B, and this guy already had A. Right? It's a broadcast medium. So instead of doing 4 transmissions, I did 3. Right? You can imagine, and I'm not going to talk about analog network coding, but you can imagine maybe that, if A and B had been transmitted at the same time, I could have done some sort of multiple access and then retransmitted that, right? And you can do that, by the way, and that's already been implemented in hardware. So it's not out there goofy. Okay, so let's talk a little bit about this. So what did we do here? We did opportunistic listening, which means every node listens to all the packets, and it stores all heard packets for a limited time. And a node is going to tell its neighbor what packets it heard. And according to the packets that it's heard, generally, it's going to go ahead and say, you can mix your packet with packets that I have heard, and I can take away the effect of the packets that I have heard. Right? In the same way that here, B, this packet was heard. Of course, it was transmitted by him, but it doesn't really matter. The point is, he knew B, he knew A, whether it was because he transmitted it or because he had heard it from some other place. And therefore, by sending A plus B, I knew that this guy would be able to get B, and then this guy would be able to get A. Right? So I'm going to use opportunistically these reception reports to tell my neighbors what packets I heard. Right? Or I can do the following, which is each node is only going to use the local information. Well, actually, yeah. So let's go with that first one, and then I'll show you something which is simpler. Each node now is going to use only the local information. I'm not going to try to do some optimization, like I showed you before. Whatever routing protocol I was using, that's what I'm going to use. Okay, so I'm just piggybacking on whatever I've got installed right now. And to send a packet P to a neighbor A, I'm going to XOR P with packets already known to A. Okay? And thus, A can decode. The question is, how can I make sure that more than one neighbor benefits? Because there's no point in my XORing packet P with packets already known to A if that packet was only of benefit to A. I could just have sent P by itself, right? What's the point of XORing it? So let me give you an idea. So here's node D, and there's A, B, and C. And this indicates the packets that are already received by that node. And these arrows here represent the demands. So C wants the slate packet and the pink packet, and B wants the yellow packet, and A wants the turquoise packet. And these are the packets they already have. So the arrows show the next hop. And this is an idea of a bad coding. I code together the slate packet and the turquoise packet. What happens is C will get the packet because it already had turquoise and it wanted slate, so he's happy. But A is not going to get the turquoise packet it wanted because it doesn't have the slate packet in its received packet set. So of course, you can look at it right away and say, aha, I should have combined turquoise and pink. Right? So in this case, C is going to get pink because it already had turquoise, and A is going to get turquoise because it already had pink. So with one transmission, I made 2 people happy for 2 different packets that were demanded. Okay? Now you see, first of all, this is not an end-to-end coding. I decode immediately. The rest of the network is not any wiser. Right? So this is the COPE system. Remember the little show I gave you this morning with the students watching movies? It was using COPE. Right. So the rest of the network is not any wiser because you basically encode locally opportunistically and you immediately decode. Right? So you're not transmitting coded packets throughout the network. There's not a complicated coding vector that's following anybody. And the only code I'm doing here is XOR. Yes?
What does COPE stand for?
Pardon? COPE?
Yeah.
Coding opportunistically, I forget. You know, so when you work with people in systems, they love acronyms, you know, which is very foreign to us, you know, as information theorists, because, you know, how many acronyms do we have? Not many, right? I mean, so we have, you know, so we have all these fun acronyms, but, you know, to be sure, they're a little, you know, you have to modify a little bit, you know. So it's coding opportunistically something, I forget, you know. But packet, yeah, no, I don't know if it's even packet erasure. There was no erasure. It's coding opportunistically. Yeah, I don't even remember. I don't think we actually even wrote it in the paper what it stands for. But I remember discussing it. So yeah, and some of them, you know, yeah. Yeah. So, you know, sometimes you look at letters that are in the middle of the word. I mean, you know, I have to say, they take liberties, okay? And of course, this is the best coding. I should have combined A, B, and C, okay, together. I mean, I should have combined the pink, turquoise, and yellow together so that all three A, B, and C would have gotten a packet, right? So the arrows to next hops, I'm going to XOR n packets where each next hop should have the n-1 packets encoded with the packet it wants. Right? So here I encoded 3 packets, and each next hop had 2 packets encoded with the packet it wanted. Okay? Very simple. I mean, it's so simple. How heuristic can you get? And you decode right away. Okay. And what does it give you? Let me just make maybe this is a bit more of a networking. Remember when I was talking a little bit before, I said, you know, these reception reports, and I said, we'll make it a little easier. The reception reports can be hard to generate. Okay? So one of the things that you might do is just use guessing. Okay? Just infer from sort of what you overheard what people have heard. And that works very well. So in the results I'm going to show you, it all uses guessing. Okay? So, in the experimental results I'm going to show you, instead of using the routing protocol that's being used is what's called, oh, it's confusing, because XOR, the way we've been using is, of course, exclusive OR, binary. But there's also XOR EXOR, which is extreme opportunistic routing, which we didn't invent. But basically, what it does is it's very simple, very elegant. S transmits. If by chance B overheard it, then A does not transmit to B. It's that simple, but it does much better than most routing schemes out there right now. And basically, you piggyback on the reception report to learn whether the next hop has the packet. And that allows you to cancel unnecessary transmissions. It's very effective. So ideally, you'd like to design some sort of collision detection, backoff scheme, but, you know, you're just going to use 802.11. That's not what it does. The main punchline is we're going to put the cards in promiscuous mode. That's not usually the way you use your 802.11 cards, right? Usually you're using your 802.11 cards to help you pretend that you're not in a wireless environment, to help you pretend that you're in a wireless environment and you have point-to-point. But we're actually going to put them in promiscuous mode because we want to overhear as much as possible because we're going to be making use of what we overhear. Okay? So we're going to embrace interference and overhearing. Okay? Okay, so here's the experiment, 40 nodes, 400 meters over 400 meters. I'm going to show you duplex and unidirectional. Okay? The metric is the total throughput. Here's the current 802.11 with no coding. This is with opportunistic listening and coding, so extreme opportunistic routing. I'm sorry, opportunistic listening and coding, and with opportunistic routing. And this is our scheme with two-way flows.
What is the line
Net throughput in kilobits per second. Can you not see it? Is it not clear on the? Okay. Oh, I'm sorry. This on the abscissa is number of flows in experiment. Number of flows that you add. And over there is the net throughput. Total throughput in the network.
Number of flows that corresponds to number of independent sources?
No, one source could have more than one flow going to different receivers. Okay, number of different flows, different flows. Okay. This is now one-way flows. This is no coding with encoding, and this is a little clearer because here it appeared to, I put it in white. I'm sorry, I should have put it in white. So over there in black, which does not have, enough. Do not play with animation is the bottom line.
And these flows are unicast?
These flows are, okay, these flows are unicast in this case. These are one-way flows here. So it's point to point. Now, the coding we're doing is fine because it's just locally coding. It doesn't care if it was multicast, unicast, who was going to where, right? It's completely opportunistic and local. And I'm undoing the code immediately at the neighbors. Okay? So the receiver actually does not see anything coded throughout the network with some impulse response or anything. It just immediately sees what it wanted to see. Okay?
So no coding actually corresponds to routing?
Yes, no coding is routing, but it's good routing. It's extreme opportunistic routing. So I'm not comparing coding to some lousy routing. But the interesting thing here is I'm basically using the routing mechanism here to create my subgraph there. So what happens? When you lightly load it in terms of number of flows, well, network coding doesn't give you that much. It's just like I told you this morning. If things are good, yeah, sure, you can code and get a little bit. But, what's the point? It's when things are bad that you really get a difference, right? So over here, your net throughput gain is rather moderate. But look over here. Look over there, right?
So would you please clarify this to me? Because I think what you're doing, you're basically creating the graph, the communication graph,
yes,
in support of the routing protocol. So you're
yes,
using the mixing part of for your combination.
See, the thing is, you're not creating a graph in a static way, right?
Dynamic.
You're dynamically using, because that's what extreme opportunistic routing does. It depends on what you overheard.
Then on top of that, you're doing your...
Then I'm just doing my opportunistic coding on top of it. What happens here in the end is that many places do not code in your network. A few places code. What happens is when you get a place that has a lot of opportunistic code, it's because that node had congestion. The more congestion you have at a node, the better coding opportunities you have, right? And the more congestion you have at a node, the more that one was creating a bottleneck in your network. So you're naturally reducing the congestion most at nodes that could use it the most. And that's what you're getting here. Okay? So it is network coding, but it's network coding of the just most basic, rudimentary sort with immediate decoding. And the sources and the sinks actually are none the wiser. They don't even know it was coded in the middle. They're not operating differently. They're not doing decoding. Right? Unless it was some cope. But you see how, again, going back to the argument before, we don't know what the optimum is to do here. We wouldn't know how to compute the optimum here. But boy, is this better than what people do now. Right? And that's, I think, the real point. Okay. So I think, whenever sometimes talking to people, I say, well, maybe if we did smarter routing, we would not need coding. Maybe if we did smarter routing, whatever, maybe I could take this a little further, right? But I think if you don't do coding in the end, you're just shooting yourself in the foot. I'm categorical about that. You just can't do it. Okay? Is everybody clear on what we did here? It's just cope. And by the way, this was with guessing. Okay, not even so. Yeah. Okay. So again, at this point, you should feel good, right? You should feel like, information theory does things for networking. And you should proudly hold your head up to your networking friends and tell them, you know what? Okay. So let's go back to the optimization, right? Remember, in the optimization, I had this very nice multicast optimization, but in general, of course, I don't even know what to do when I have non-multicast. But it would be nice to say, well, can I at least use coding, starting from the multi-commodity flow that uses no coding, could I at least use coding to do at least as well as a combination of multi-commodity flow and standard trees? So I don't even know what that problem is called because I've never seen it, but it would be sort of the arbitrary, sort of the Uber problem where I have some multicasts and I have some point-to-point flows, and the whole thing comes together, right? How would I optimize that? I don't know. I don't even know what it's called. But could I at least relax it using linear codes and do no worse than I did before? This goes back to let's do no worse than I did before. And it turns out that a solution of the problem implies existence of a network code to accommodate the arbitrary demands, and the types of codes subsume routing. Okay, so you can show that you can relax the integrality constraints in this sort of bizarre combination of standard trees and multi-commodity flows, where they both have to coexist, the standard trees and the multi-commodity flows. And you could use a linear code construction that's guaranteed to perform as well as routing, at least as well as routing, by removing some integrality constraints. Okay? And but you have to put a couple constraints. First of all decoding is going to be performed at the receivers, which is fine. Right? Obviously, when you're not coding, it says so all decoding is performed at the receivers. Of course, I'm restricting myself to linear codes. Yes?
When you say that this, by using network coding, you come to the problem which is no longer NP hard, the scaling problem still remains hard problem.
No, it is NP hard because in the, a special case would be I just have a multicast. This is NP hard.
I meant the scheduling part, even for
The what part?
the scheduling.
The scheduling, yeah.
If you have like the typical models used by memory community where you want to, let's say, solve an independent set problem every time it's not to support emulation. That's a hard problem.
Yes, it is a hard problem. So it is hard. Yeah. So we agree, it's hard. Right? I mean, I don't know if I quite understand your question. So what I'm saying is, can you speak up actually? Okay, let me give you the mic. So we shall give it by the network coding. Yeah, let's see. Honest middleman finding the lowest cost. Oh, look at that. It works as advertised. Bellman Ford would be so happy. Bellman, yes.
I think a couple of topics earlier, you were talking about the standard problem.
Yeah.
Which using network coding you can convert into a problem which is no longer a standard problem.
That's correct.
And which is a polynomial.
Yes. Yes, very good.
But that problem, I was just wondering if the scheduling part of this new problem is still.
The scheduling part.
The scheduling part, as in if you want to decide which set of users can transmit, are allowed to transmit at the current slot, and if you have these kinds of constraints, like the one goes by A2.11, where if someone transmits.
Okay. So it's not really related to this, what you're asking.
Yeah, I mean, it's part of this problem.
So let me try to see if I understand the question that you have asked. You're asking, if I have, for instance, so of course the scheduling comes in if I have some sort of constraint. No, you can sit down, I got it. Okay. If I have some sort of constraint where say 2 users, if there's interference, 2 users are talking to 1 user, or 1 user has to choose which link it uses because there's a constraint on this transmission, right? Okay. So the network coding does not get rid of the NP completeness of the scheduling. Is it not? It was off. Was it on? I guess psychologically, just standing up made you louder. Okay. So anyway, so so you can have a scheduling problem with network coding. It does not get rid of scheduling issues. It does not get rid of scheduling issues because, in effect, what you have with the scheduling is you have an integrality constraint which does not come from the coding. Right? It has a constraint of the type I can only transmit or receive, for instance, say full duplex constraint. So those integrality constraints, if they're there, the coding does not get rid of them. Right? So it does not get rid of those types of constraints. Right? If I have time, I'll talk actually a little bit about this issue in terms of some representations that you can make for that. So it's a good question, I understand it. But it's a little different from this one right now. Right now I'm not looking at scheduling. I'm just looking at a problem which would subsume doing the best Steiner trees combined with the best multi-commodity flow, which would be what routing would do in the absence of scheduling conflicts. Okay, good. So is everybody happy with what I'm doing here? Okay? All right. So here's my optimization. Well, it doesn't look very bad. Okay? I mean, really, right? It doesn't look very bad. My goodness, you know, the Steiner tree, multi-commodity flow, the whole thing together, it looks so clean. So let me tell you what it does. So I'm minimizing again a cost. Let me call it right now a linear cost. It doesn't really matter that much. Z, as before, is my physical flow, subject to being less than some sort of capacity on a particular edge. And the Z, which is this virtual flow, is this animal here, which is a sum of Y's, where these Y's are some sort of one more level of indirection. And this level of indirection is that these Y's have to be greater than, this is the benefit on link ij for terminal T and process M. Right, so remember before we had benefit along link ij to terminal T, because it was multicast, it was only one process. This is link ij terminal T. Okay? And what's the C over here? Well, this C over here is actually, it's a partition, okay, of the processes that represents the sources that can be mixed or combined linearly on links going into J. So I combine linearly. For each set of combinations, I get a Yij, which is the combination that I did. And then there are the things I did not combine over. So those have to sum up to the physical flow. So the physical flow is the sum of the combined processes. The ones that do not combine together add up. Makes sense, right? I have 2 bits. I combine them into, I sum them up, it gives me 1 bit. I don't sum them up, I still have 2 bits. That's all this is saying, right? And I have my degrees of freedom. Conservation, just like I did before. Okay? For receiver T, process M, my degrees of freedom coming into J have to equal the ones going out of J, except, of course, if I'm at a source or a receiver. And it will depend on RM because I have different processes. You see what I mean by this combination of multicast and point-to-point? Right? RM could be from one point to another, to just one point, or it could be from one point to several points. Right? I can do whatever I want. So, okay, so this is it. So why bother? Am I done?
Sorry, what's capital D?
Pardon? What's capital D is the set, is demands, thank you. This was not planted. Capital D is a set of demands at T. Okay? All right. So here you go. Am I done? Pardon? Is this going to be, so am I done? Polynomial, I mean, certainly I don't have a ridiculous number I have a small number of constraints, right? Life is good. They are linear. I mean, the constraints by themselves are highly benign, right? So is it? Is, the general problem, as long as I restrict myself to linear codes and I allow decoding only at the receivers, this is guaranteed to do at least as well as any routing, any combination of multi-commodity flow, standard tree, anything you come up with. Is there a trick? Obviously, otherwise I wouldn't be asking. What's the trick? Why is this? So remember, in the multicast case, it was a piece of cake. Is this a piece of cake or not? And if not, where is the partitioning bothers you? Ah, yes, the partitioning should bother you. What does it bother you?
Because we don't know which of the bits we want to combine. Which of the
That's it. Yeah. Oh, I was hoping for a little more suspense. No, that's good. That's good. All right. Anyway, that's it. The partitioning should bother you. Basically, what happened is I do have an integrality problem. It's right here. Whom should I combine together? Right? How do I create my C? So remember, the standard tree problem, the thing that makes it NP complete is deciding which nodes. It's not figuring out the whole tree. It's deciding which nodes I'm going to go through that are not receivers, which is why standard tree is difficult and spanning tree is easy. Right? So here, it's the same thing. This partitioning, this is discrete. This is where it's hard. Okay? But if you gave me the partitioning, if you told me I can only encode these guys with these guys, if you gave me that constraint, bam, this does it. Right? But a priori I may not have a constraint, and I could have an exponentially large number of possibilities. Right? Because I have, say, k processes, whom am I going to, I'm going to have an exponential growth in terms of whom I combine with whom. Okay, does that make sense? Okay. Okay. So that's what I said. So it's basically just the optimization, the code. Anyway, it doesn't matter. Let me see. Until when do I go again? 15 minutes. Oh, I've been okay. So what do? Delay, security. Oh, delay or security? Okay, how many delay? How many security? Oh, that didn't work. Okay, so, the problem is that somehow there's like these two groups, and the delay group is in, the security group's like that. Okay, so delay, either, okay, so, oh no, you can't get, security. Pardon? What do you think? You think security? Okay. Yeah. You know who to blame afterwards. I'll delay people. Talk to Professor Lacuche afterwards. Oh, this was so beautiful. Oh, the animation we're missing. Oh, and the economic implications and the file downloads. And there we go. All the scaling laws I told you I would tell you about. Okay. Security. So now we're putting operates by allowing mixing of data. So for a security person, you would say, you did what? You allowed your nodes to take data and randomly mix it and send it out? Oh, you're nuts, right? Literally, right? Because now I put in one bad packet in my network, and it's going to mess everybody up. Everybody, right? Oh, no, not everybody, but a lot of people, because I've allowed the mixture. So what are the security consequences of such mixtures? I'm going to go very briefly over three aspects. One, which is the wiretapping aspect. Also, I want to and not at the very end so that we have a little time for discussion. The other one is Byzantine or pollution attacks, and I was talking, I think, with Sylvia about error correction. This is going to cover a little bit of that. Detection and correction. And the other one is just verification. So let me look at the first thing. So if you have a mixture of two messages appropriately compressed, it makes one message a one-time pad to another. Remember, we mentioned this before when I said, well, what happens if you lose one of the packets, right? The other one is the sum of the other two packets is a one-time pad to the other. So if I want such mixtures, we can derive limits on network capacity. So basically, this was that was something that Tsai and Young pointed out, and that the other one is resolved by Feldman et al. In general, it's difficult to know the maximum number of links that can be tapped by an adversary, and you may not be able to do such coding schemes because there may be places where, well, you didn't get to mix with anything yet. You're all by yourself. Okay? So you can consider schemes with more progressive measures of security, and you can consider the cost of security. So basically, the idea is the following. You can use disjoint paths for data transfer, and you can use other messages for encryption. Again, this one-time padding. Now, caution here. When we're talking about one-time padding, it means that I'm assuming that I have perfect source coding. Right? I mean, if I have a message that's like all zeros with every so often a 1, not a good one-time pad. Okay? So, yes? Adam?
You're also assuming that the person you're bothering to protect against doesn't know much about the message you're compressing.
I'm assuming that the person, well, obviously if they know the message, then, why are they wiretapping?
No, the one you're using is the one that
That's correct. That's correct. Right. The one that I'm using. Absolutely. Absolutely.
In general, even if they know a little bit about it, and your compression algorithm knows less.
That's correct. That's correct. So there are issues. That's absolutely true. That there are issues there. But let me give you some idea. I mean, in some areas of applied security, people consider dispersive routing, bless you, to try to avoid too much of a traffic to be basic. This does not replace, let me put it this way, I'm not suggesting that this replace cryptography, right? I'm saying that compared to something like just dispersive routing where you're saying, I just don't want the attacker to observe too much of my data, even though it's encrypted, possibly. This gives you a lot of benefit over something like dispersive routing. Okay? So if you send no other messages, it's basically, as I said, identical to dispersive routing. If other messages are sent, you get extra security from network coding. All right? And the fact is you can send the security via network coding lower cost than with dispersive routing. And if you define the level of security provided by random linear code as the number of symbols that an intermediate node has to guess, right, you can map a key size to the number of bits that you have to guess. So even if, suppose, you may know something about what I compressed, you still will have to guess a certain number of bits, right? If it's a large file, that number of bits may be very large compared to the key size, which you could also have guessed. Right? I mean, the key sizes are not generally massive. Right? Anyway, that's all I'm going to say. I'm not really going to go much into this. So let me talk a little bit about, so I stop at 3:30, is that right? Okay. Byzantine attacks. And the Byzantine attacks are the most scary in a way. Because it goes back to this idea of what happens when you do a mixture. Right? If a node in the middle of the network does a mixture wrong, tells me that he did this, but did something else, send me gobbledygook. The decoder is going to think that he had enough degrees of freedom and is going to decode the whole thing wrong. Right? So all I need is one bad node in the middle to mock up the whole thing. So it's called Byzantine because of the Byzantine generals problem. How many people have heard of the Byzantine generals problem? Oh, so about half. So the idea is the following. So, we're two generals. We're trying to figure out whether to attack in the morning or not, right? So let's see, Ali's my other general, and I say, Ali, we're going to attack in the morning. So I send a messenger, right? The problem is the messenger can get killed, captured, bribed, right? Who knows, right? And Ali sees whatever he saw, and he answers, he says, yes, let's attack in the morning. But then I said, you know what? The messenger that he sent back to me could have been bribed, killed, and then captured and replaced. So I actually don't really know. So then I sent him another messenger. It's like, so it's really right? We attack in the morning, right? He's like, yes. I'm like, oh, but it could have happened that. And so we can keep going this way. We'll never for sure know, right? That we've agreed, right? So you can see why this happens in networks. Why does this happen in networks? Well, you may have a node that just is flaky, but you can also have a node that's a traitor node. It's very difficult in general to deal with traitor nodes. So this was a problem that was originally looked at by Radia Perlman all the way back in '88. She was the first one to come up with this idea of the Byzantine network, and people have looked at it since then in a variety of settings. But generally, the way it goes is the following, roughly. I try to figure out who's bad, and then I try to quarantine him in routing schemes, roughly. Okay, and I have some probability. You can imagine, right, what's going to happen here is I'm going to have a probability eventually that it's unlikely that all the messengers were bad in the same way, and I'll have some belief that we did agree. Right. So it can be arbitrary behavior. It can be dropping packet, misdirecting packet, sending spurious information. By the way, these things happen right now in peer-to-peer networks. So, not that anybody in the audience would do it, but if you're downloading illegally a movie, there are people who make a living out of putting bad movies out there. Not bad as in, lousy movies. There are people who make a living making lousy movies too. But suppose the movie is, not good or not lousier than whatever it was. People will put wrong data so that when people go and try to download these movies, the data will be mixed in, and you will get, a lousier construction. Pardon? We'll talk about hash codes later. Right. That's right. So that's what for something like BitTorrent would do, right? It would check. It would have a hash code, but then it would have a central authority that it goes check, trusted authority, right? Okay. Okay. And we'll talk about that in a sec. So what are we going to do? So what I'd like to do is have a distributed randomized network coding that can be extended to detect the Byzantine behavior. So remember, if nothing came out of this whole day, is that the roots, okay, there are only so many roots, and if your field size is large, it's hard to hit them, but it's hard to, when you're looking for the roots, it's hard to get them. Right? So when you're not looking for them, it's easy to avoid them, but when you're looking for them, it's hard to get them. Right? So this is what we're going to do. We're going to have a small number of hash bits, which is going to be a simple polynomial function of the data. So it's going to have a certain number of roots. And basically, to compute the hash bits correctly, you have to hit the roots. So if you have a traitor node inside the network, that traitor node is going to have trouble doing that unless he knows all the data. Right? Because you can be off by 1 bit, you're not going to hit the root. So it requires only that the Byzantine attacker does not design and supply modified packets with complete knowledge of other nodes' packets. Again, just a little bit unknown is enough to make it such that the traitor node cannot get past you. So the main schemes are following. Use a polynomial hash. You have an attacker without full knowledge, and the hash can be used to detect an attack. And later I can show you can do a little bit to decode also. What am I doing? Oh, I'm sorry, I repeated some slides. Anyway, so the idea is the following. I have a set of data symbols, x1 to x theta, and I'm going to have a set of hash symbols. And I'm going to have a polynomial function, so I'm going to look at symbols k by k, not a sliding window, a chunked window, k by k, and the polynomial hash is going to be x1 squared, say, through xk to the k plus 1. But you know what? You could use any old polynomial. Who cares, right? This is just a nice one. Okay? And of course, with a little bit of stuff for edge effects at the end. Anyway, so the total overhead that I'm going to have is theta, which is the total number of data symbols over phi, which is the total number of hash symbols. All right? So it trades off overhead with probability of detection. How does this work? Well, if the receiver gets S genuine packets, not S out of a certain number, S. Okay, so S could be 10, and the number of packets could be 1,000,000, it could be 100. It's the absolute number of genuine packets that are received. Now, remember, if everybody's a trader, you go home, right? So there has to be at least somebody that gives you some packets that were not affected. Otherwise, there's nothing you can do. Right? In that case, the probability of recovering is going to be at least 1 minus k plus 1 over q, which is the field size, to the s. That means that, suppose that k was 50 with a 2% overhead. So the larger k, the smaller the overhead. It's the inverse of the overhead. And a code length of just 7. And just 5 good packets. The probability of detect is 98.9. 99% with 1% overhead, a tiny little code length, and just 5 good packets. I could get 5 good packets out of, 5 million packets. It doesn't matter how many bad packets I have. Okay? So the probability that you're going to be able to detect a Byzantine attacker is huge. Now to correct, I'm going to go into detail, but to correct, it may be, oh darn, I shouldn't do this. Anyway, so to detect, all right, well, whatever. To detect, what I'm going to do is I'm going to add, so that's what to do. To correct, I'm going to have this overhead, and then I'm actually going to do something which is, in effect, like an MDS code. And I'm not going to go into detail, obviously, where, well, whatever, you can do it all. So as long as the attacker doesn't have more than half the bandwidth, you can do the MDS code along with a majority voting with the little Byzantine detection that I showed you, and you can correct it. And you can generalize pretty much all sort of coding bounds, most coding bounds. And if you look for a very nice generalization of this, I send you to Shishang and Cotter this year and also last year. Okay? And they basically take this approach and just generalize it. And they can find all sorts of, singleton bound for coding end-to-end. For you coding enthusiasts in the audience, absolutely go for it. All kinds of really, really fun things to do. So I'm not going to do the content distribution. I'm just going to the content distribution detection. All I want to say is that you don't need to receive all the packets. You can actually do a packet by packet verification, even if you cannot decode that packet. Okay, there are algebraic ways of doing that. Okay, so can I detect? So these are future directions, such as, I was trying to put some future directions which were not too weird, but which would be sufficiently interesting. The first one is, I would really love to see a real TCP-like suite for network coding. Okay, if it's going to happen, we have to do this. Okay, and it doesn't mean that we have to sort of mimic TCP in some slavish way, but it has to have its flexibility, it has to have its ease of use, and maybe it has to be at least something that we can pretend to the higher layer is still going on, right? Because so many applications are really expecting TCP. One of the things, of course, because we didn't do the distributed compression, can we create mirror size using network coding principles? Instead of having real copies, can we have partial copies and use network coding? This is something that interests me a lot recently. What's the right interaction between network coding and the physical layer? I didn't really talk about it. I mentioned briefly that maybe you can do some analog network coding. There's some demonstrations for it right there. I think that's a very rich, very, very fun area. What are the full security implications of network coding? I talked a little bit right now about some of the implications in terms of data hiding, data correction, detection of attacks. But it opens up so many problems, but also gives you so many different solutions to what we've been doing all along. And finally, it's kind of a bit of a philosophical question. how do I design a system? I mean, most of what I showed you today, pretty much everything was, I have a system, I'm going to put network coding on top of it. How would I design the system if I started out saying I'm going to do network coding on it? Right? How would I design wireless networks? How would I design wired networks, assuming network coding? Right? And we didn't talk about network coding for routers and switches. There's some stuff there. And actually, I was hoping that I would get to that, and that would have gone to your question of the scheduling, okay, that you can do there. Okay. Anyway, so this is these are some of the future directions. And my hope today was, for those of you who are already looking at network coding, to maybe show you some other aspects that maybe you weren't as familiar with or hadn't considered. For those of you who had no interest in network coding, my hope is that I'll show you that it really has connections to so many things, just so many things. So, you know, whether you're sort of a capacity junkie, or whether you're a coding junkie, or whatever it is, you know, whatever your particular information theoretic vice is, apply it here. Okay? It's a great place to do it. And that's it.